Welcome back to the lecture series on data structures. In this lecture, we look into the algorithmic part of AVL trees. So how do we achieve balance if there is a loss of balance? Let us see the algorithm part of that. So in the first case, we look into the LL rotation case where the vertex is added in the left subtree of a vertex y, because of which y has lost its balance. In such case, we need to identify three vertices: the vertex y, which has lost its balance, and the child of that as x, and the right child of x as t2 as the right child of x. So in the LL rotation, to achieve the balance, what we do is we'll rotate the tree on the right side on the vertex y. That means we'll push x upwards, and we take y as the right child of x, and the already existing right child of x, t2, that is added as left child of y. So how do we achieve the actions here is so right rotate on node y is achieved by taking x as left child of y, t2 as right child of x. Then we perform the rotation by taking right child of x as y and left child of y as t2. And once we push these nodes, we re-update the balance factors. To achieve the balance factor, to calculate the balance factor, we need to update the heights. So we update height of y recursively, of course, as max of left child of y, comma height of left child of y and height of right child of y plus 1, and height of x as max of height of left child of x, comma height of right child of x plus 1. So we will update the heights also and return x. That means after rotation, the balance factors are updated and the value x is returned for further processing. So this is what the right rotation is. So if we implement here, 15 is a vertex which has lost its balance because of addition of 5 and the left subtree of y. And the left child of y, 15, is 10, and the right child of x is 12, that of 10. Now if we rotate, 10 becomes the root node for this part of this tree, and y becomes 15 becomes the right child of 10, and the right child 12 of 10 becomes the left child of 15. So this is how we achieve the right rotation. Now we look into another case, RR rotation, where here the balance of x is lost because of addition of a vertex in the right subtree of x. Here the vertex x has lost its balance, and y is right child of x, and t2 is left child of y. This is the scenario. If this is the scenario, what we do is we'll left rotate the entire tree based on x. That means we push y upwards and take x as left subtree of y, and the left subtree of y shall be taken as the right subtree of x. This is how we achieve the balance. We perform this in the form of a functionality here, left rotate on x. So we identify y as right child of x and t2 as left child of y, and to perform the rotation, two actions are performed. Is left child of x is equal to, sorry, left child of y is equal to x, and right child of x is equal to t2. Once we update this, we update the heights of both vertices, because we have changed their position as max of height of left child of x, comma height of right child of x plus 1, and height of y as max of height of left child of y, comma height of right child of y plus 1. Because these heights are calculated recursively, of course, because it is involving again height of left child of y. So they will be calculated recursively for the entire tree once these functionalities are called, and we'll return y because that is a topmost vertex in this part of the tree. The LR type of rotation, where the balance is lost because of addition of a vertex v as the right child of left subtree of a vertex a. In this case, 30 is the vertex which has lost its balance because of addition of 27 in the right subtree of left subtree of 30. Now, how do we achieve the balance is, first we left rotate on the vertex 30 and then right rotate on the vertex 30. In the previous lecture, I directly gave the answer to be that 25 has to be made as a pushed up, and 30 should be the right subtree, and 25 should be 20 should be the left subtree of that. Like this we have given the solution. Now that actually can be achieved as a combination of two rotations. One is left rotate on vertex 20 and then right rotate on the vertex 30. So in the first case, if we left rotate on the vertex 20, we push 25 upwards, just like in the previous slide. We push 25 upwards and 20 will make 20 as a left child of 25. So the 27 becomes the right child of 25. And at this point of time, 30 and 40 are undisturbed. But still the balance is not achieved, and still 30 has imbalance of +2. Then after this we right rotate on vertex 30 so that 30 is pushed down and 25 is pushed up. So 25 is pushed up, 30 is right child of 25, and the right child of 25 is made as left child of 30. 27 is made left child of 30. So after this the balance is achieved. So the LR rotation is a combination of left rotation on 20 and right rotation on 30. That is left rotation on left child of 30 and right rotation on 30. Based on this we can build the algorithm. The last case is RL rotation, where vertex A has lost its imbalance because of addition of a vertex V as part of the left subtree of right subtree of A. So in this case 40 is the vertex having a 20 and 70 as the left and right children, 50 and 30 are the left and right children of 70. At this point of time tree is perfectly balanced. Now if I add a vertex 45 as the left child of 50, that is added as the left child of right child of 40, because 40 is the latest ancestor which has lost its balance because of this addition. So vertex AA can be treated as 40 here, and which has lost its balance, and because of addition of a vertex in the right subtree of left subtree of 40. Now how do we achieve the balances? We'll first right rotate on the vertex 70, which is the right child of 40, and then the left rotate on 40. So if I go for the right rotation on the right child of 40, that is 70, we push 50 upwards and 70 downwards as the right child of 50. So 50 is pushed upwards, 70 is made as a right child of 50, and 80 is the right child of 70. So this is the first scenario. Then we left rotate on 40 in the second step. That means we push 50 upwards and make 40 as the left child of 50, and the right child of 50 is made as left child of 40. So this is the left rotate on 40. Because of these subsequent operations, the balance factors are recalculated and it is observed that balance is achieved. Again, the main point here is this RL rotation can be observed as a combination of two rotations. One is right rotate on the right child of vertex 40 and then left rotate on 40. Now we look into the algorithm for insertion of a node into the existing AVL tree, and how insertion of a node is going to create imbalance, if at all it is going to create an imbalance. We have seen how to achieve the balance. So let us see the algorithm for this. Now insert node comma key. Node is a tree starting with vertex of the tree, and key to be inserted. By chance, if given node itself is null, that means no AVL tree is present, then first we will create the node. Node is equal to create node, and data of node is equal to key is inserted and return node. That's it. So if no tree is there, just we insert the data and return the node. If this is not the case, either the two possibilities are there: key may be less than the existing data of the node, that is one case, or key may be greater than data of the existing node. Now if key is less than data of the existing node, we need to perform the insert operation on, again we call the function on the left child of the node. So if key is less than data of node, left child of node is equal to insert on left child of node comma key. So we push down and observe the insert function on the left child of node of the key. The value is returned as left child of the node. Else, if key is greater than data of the node, that means key is in the right part of the existing node, then right child of node is returned as insert. Again, we call the insert function on right child of the existing node comma key. Else return node. So if these two cases fail, then just return the existing node. Then moving forward, we update the heights. Once we perform the insert, we need to update the height and the balance factors. How do we update the node? Height of the node as 1 plus maximum of height of left child of the node comma height of right child of the node. Again, these are recursively calculated on each addition. Similarly, once we calculate the height of the nodes, we calculate the balance as if n is equal to null, balance is 0. Otherwise, balance is equal to height of left child of the node minus height of right child of node is calculated the balance. So again, these balances calculated recursively. Once we calculate the balance, there are 4 cases. If balance can be lost in 4 cases, as we have seen in previous slides, they are observed here. If balance is greater than 1, that means it may be 2 or more plus 1. Balance is greater than plus 1, so balance may be plus 2 or more. And the key is less than data of left child of node. That means the given key shall be present on the left side of left child of node. That is LL type of rotation here. So how do we achieve the balance? We right rotate on the node. So return right rotate on node and balance is achieved. The other case is balance is less than -1 and key is greater than data of right child of node. What do you mean by that? Balance may be -2 or more, -3 or so, minus greater than -2, and key is greater than the right child of node. That means key should be present on the right side of right child of node. This is RR type of rotation. So to achieve the balance, what do? We go for left rotate. So return left rotate on node. Third case, if balance is greater than 1 and key is greater than data of left child of node, that means balance factor is +2 or more, and key is greater than data of left child of node means the key is added, vertex is added on the right part of the left child of node, right? So this is again RL type. Then how do we achieve the balance? We achieve the balance with a combination of 2 rotations, of course. First, we left rotate on the left child of node, and then on that we perform the right rotate on the node. So because of the combination of these 2 rotations, as we have seen in the previous slides, a combination of 2 rotations are performed and balance can be achieved. Now the fourth one is if balance is less than -1 and key is less than data of right child of node. That means balance factor may be -2 or -3 or something like that, and key is less than the right child of node. That means it is added in the left part of right child of the node, right? So it is RL type of case. Then how do we achieve the balance? Again, as we have seen in the previous slide, it is a combination of 2 rotations. First, we perform the right rotate on right child of node, and then we perform the left rotation on the node. So once we achieve these 2, we'll get the balance. So these are the 4 cases. Once we calculate the balance factors, these 4 cases may arise, and based on the balance factor and the observation on key, we can perform any of the 4 cases. Once this is done, just return the node. Actually, this is a recursive algorithm because while inserting, we are calling on insert on left child of node if key is less than that, and if key is greater than that, we are calling on the insert again on the right child of the node. So this being a recursive algorithm, whenever a new node is added, all the balance factors and heights are recalculated, and based on the balance factor, these 4 cases can be observed, and with the addition of these rotations, balance can